This topic is control system instrumentation, and you will remember in the previous topic when we introduced the feedback controller, the PID feedback controller, and we considered a motivating example of a blending process, there were several other units in the feedback loop besides the controller itself. In particular, we had an instrument that made a measurement of the composition. We had a transmitter that transmitted that signal to the controller. And then after the controller, we had a control valve. Okay, all of those elements will have an effect on the performance of the controller, and it's important that a control engineer have some understanding of how the other elements in a feedback loop, besides the controller itself, behave. Okay, and so that is the purpose of this topic. The first thing in most control loops is a sensor, which makes a measurement of the variable that is going to be controlled. And there are many different technologies that are available for making most kinds of measurements, and control engineers are sometimes called upon to select an instrument for making a particular measurement. And there are a number of factors that can be considered, and some of them are listed here. The first is measurement range or span. That's the range of values of the measured variable that the instrument can make an accurate measurement. Some instruments can only provide an accurate measurement over a narrow range of values of the measured variable, and others can provide an accurate measurement over a wider range. Of course, you'll want to make sure that an accurate measurement is possible over all of the entire expected range of values of the measured variable. Performance, of course, is a critically important consideration, including accuracy, repeatability, and speed. Accuracy, of course, refers to how accurate or correct the measurement is. Repeatability refers to the ability of the measurement device to return the same value for the measured variable under the same conditions. And speed may not be a critically important factor for a laboratory measurement, but for process control applications, the speed with which the measurement can be made is a significant consideration. If the measurement can be made quickly, control performance will improve. If the controller has to wait several minutes or more, if there's a lag of several minutes or more for the measurement, that will result in decreased performance of the controller. Okay, reliability is also a critical consideration. Most continuous processes operate 24 hours a day, 7 days a week, 365 days a year. If the measurement instrument fails, then control will not be possible until the instrument has been replaced. Materials of construction are an important consideration in terms of reliability and in terms of compatibility with chemicals that may be present or may come into contact with the instrument. Prior use refers to your own experience with measurement technology or your company's familiarity with certain measurement technology. Some companies always use the same kind of instrument for making a particular measurement, and in that case that may be preferable since engineers and operators are already familiar with that particular kind of technology. Safety, of course, is always an important consideration when it comes to process control and making measurements. Whether the measurement is invasive or non-invasive is also a consideration. An invasive measurement is one in which an instrument or probe is inserted directly into the process, and a non-invasive measurement is one where that's not necessary. And then, of course, cost is also an important consideration. The instrument, the sensor that provides the greatest measurement range, the highest performance, the best reliability, is probably going to be the one that's the most expensive. So there's a trade-off between cost and all of these other performance factors. This table shows different technologies that can be used for different types of measurements. For the purpose of this course, we're not going to go through each one of these and explain what all of them are. The takeaway message from this table is just that there are many different ways of making different types of measurements. And there are different trade-offs, as discussed on the previous slide, between using different technologies with various levels of sophistication, accuracy, reliability, cost, all of the factors that were mentioned on the previous slide. Okay, so that's all that we will say about sensors. After a signal has been measured, it's necessary to transmit that measurement to the controller. And for that purpose, we have an instrument that is called a transmitter. A measured physical property, such as temperature, should be converted into an electrical signal for transmission to the controller. A typical standard for a transmitter output is a range between 4 and 20 milliamps. Okay, this is somewhat arbitrary. It's become a standard over the years for process instrumentation. You might wonder why the minimum value of the current is not 0. The answer is that we want to be able to distinguish between a low signal and a failed instrument or a short circuit. So if the valid values of the output range were between 0 and 20 milliamps, and we were sitting in the control room and we saw a signal of 0 milliamps, we wouldn't know whether the measurement was below the low value or the instrument had failed and there was a short circuit or something like that. So we use a non-zero value for the minimum. Minimum value is 4 milliamps. The maximum value is 20 milliamps. And in between 4 and 20 milliamps, the signal scales linearly with the unit that's being measured. Okay, so here's an example. A temperature transmitter, temperature measurement device, and associated transmitter may have these outputs. Okay, the minimum measurement value is 50 degrees centigrade. The maximum measurement value is 150 degrees centigrade. So if the measured temperature is 50 degrees or less, then the output is 4 milliamps. If the measured temperature is 150 degrees or more, then the measured output is 20 milliamps. And if the temperature measurement is between 50 and 150 degrees centigrade, then the output signal scales linearly with the temperature over this range. Okay, we can define a gain for the measurement element. Just like we defined a steady state gain for a process, we can define a gain for this measurement element. Take a moment and think about how we might do that and how we could calculate the measurement element gain for this particular temperature transmitter. Okay, assuming that you have thought about it for a moment, the answer is that we can define a measurement element gain by dividing the range of the output by the range of the input. So we take the range of the output is 20 minus 4, and the range of the input is 150 minus 50. And so the measurement element gain is 0.16 milliamps per degree centigrade. As for a process, the measurement gain has units of the output variable divided by the input variable. In this case, it's the electrical signal units divided by the units of the process variable that's being measured. So for each 1 centigrade increase in the measured temperature, the electrical signal value increases by 0.16 milliamps. Okay, the last element, besides the controller, that's commonly encountered in a control loop is a control valve. Okay, there are many ways to manipulate flow of material in a process. For example, the speed of a pump, blower, or compressor can be adjusted. But the simplest and most commonly used method for controlling flow in a process is to use a control valve. As we said, control valves are often pneumatically actuated, and they can be designed to be either air to open or air to close. An air to open valve means that as the air pressure increases, the valve opens, And an air to close valve means as the air pressure increases, the valve closes. And the choice between these two depends primarily on process safety considerations. In particular, we consider what we would want the valve to do in an emergency if the air pressure signal was lost, if there was a break or a leak in the air pressure line. In an emergency situation, would we want the valve to open or close? If we're talking about cooling water to a chemical reactor, in an emergency situation, we probably want the valve to open, and therefore we would choose an air to close valve. So if the air signal was lost, if there was a break or a leak in the air transmission line, the valve would open, the reactor jacket would be filled with cooling water, and the reaction would hopefully be quenched. By contrast, if we're talking about the feed to a chemical reaction, we probably want that valve to close in an emergency, and so we would choose an air to open valve. If the air pressure was lost for some reason, the valve would close, reactant would no longer be fed to the reactor. Okay, this is a schematic diagram of a pneumatically actuated control valve. This is the actuating signal, a tube or pipe containing air that can be at a different pressure. This top part here is called the valve head. It includes a diaphragm and an actuator spring. The diaphragm can be deflected up or down, and as the diaphragm is deflected up or down, the valve stem rises or falls. Okay, down here is the valve itself, including the valve seat and the valve plug. And you can see as the valve stem rises, the valve opens, and more fluid can flow through the valve. The actuating signal is introduced here, so if the air pressure increases, the diaphragm will be deflected upwards, the valve stem will rise, and the valve will open. The valve position indicator is a physical indicator indicating the valve stem position, so if you are looking at the valve, all this part is sealed up, but you can still see the valve position indicator. You can tell by looking at the valve how far open or closed the valve is. Okay, since the actuating signal enters on this side and increasing the air pressure will cause the diaphragm to deflect upwards, this is an air to open valve. If I were to connect the air signal on the other side, then I would have an air to close valve. Okay, specifying control valve properties is not always easy. Another task that control engineers are sometimes given is to determine an appropriate size for a control valve. A very rough heuristic, an approximation based on past experience, is that the valve should be sized so that it is 50% open and accounts for between 1/4 and 1/3 of the total pressure drop in the line at the nominal operating condition. Okay, it makes sense that we would want the valve to be 50% open under nominal operating conditions. This heuristic here, that the valve should account for between 1/4 and 1/3 of the total pressure drop in the line, represents a trade-off between two factors. On the one hand, if the valve accounts for a very small fraction of the total pressure drop in the line, it will be difficult to control the flow rate by adjusting the valve position. If the valve accounts for only 2 or 3% of the total pressure drop in the line, then opening the valve will result in only a very small increase in the flow rate. We'll have very poor controllability. By contrast, if the valve accounts for a large fraction of the total pressure drop in the line, say 70% or 80%, then you have a very significant pressure drop over the valve that corresponds to energy loss. You need to pump the fluid up to a high pressure only to waste that energy when the pressure is lost over the valve. So this heuristic represents a trade-off between controllability and energy consumption. Heuristically, the valve should be designed so that it accounts for between 1/4 and 1/3 of the total pressure drop in the line. This will allow for reasonable control without wasting more energy than necessary. Okay, control valves also have a property which is called the flow characteristic. the flow characteristic describes the relationship between the lift, that's the position of the valve stem, remember the schematic diagram we saw previously, the position of the valve stem and the flow through the valve. Depending on how the valve seat and the valve plug are designed and shaped, we can have a different relationship between the lift and the flow. Three common choices are a linear relationship like this, an equal percentage like this, and a quick opening or square root relationship like this. And those are shown mathematically here. And the relationship between the flow rate through the valve and the lift, the relationship between the lift and the flow rate through the valve, is given by this expression, where CV is the valve coefficient, F of L is this flow characteristic, delta PV is the pressure drop across the valve, and GS is the specific gravity of the fluid, which is the density of the fluid divided by the density of water. Okay, the equal percentage valve might seem like an unusual choice. It has the property that dF dL is proportional to F, so there is an equal percentage change in the flow rate for a particular change in the lift L. Okay, all of this might seem kind of abstract. We'll consider an example on the next slide. Here is an example of sizing a control valve. A pump furnishes a constant head of 40 psi-G over the entire flow rate range of interest. After the pump is a heat exchanger, and the pressure drop across the heat exchanger is 30 psi-G at a flow rate of 200 gallons per minute, and can be assumed to be proportional to the square of the flow rate. The pressure drop is proportional to the square of the flow rate through the heat exchanger. You are asked to select the rated valve coefficient that determines the size of the valve and plot the installed characteristic for two cases. The first is a linear valve that is half open at the design flow rate, and the second is an equal percentage valve with a value of capital R equal to 50 that is sized to be completely open at 110% of the design flow rate. Okay, take a moment and consider how you can solve this problem. Okay, assuming you have thought about how to solve the problem, it is helpful to first determine the pressure drop across the heat exchanger and the valve as a function of the flow rate. We were told in the problem statement that the pressure drop across the valve was equal to 30 psi-G when Q was equal to 200 and was proportional to the flow rate squared, and so the pressure drop across the heat exchanger can be described by this equation. The total pressure drop in the system is 40 psi-G, and so the pressure drop across the valve must be 40 minus this quantity. So we can represent the situation graphically here. This curve shows the pressure drop across the heat exchanger as a function of the flow rate of fluid, liquid, through the system. And the distance from this curve to this line indicates the pressure drop across the valve. So as the flow rate through the system increases, the pressure drop across the heat exchanger increases, and the pressure drop across the valve decreases. Okay, it makes sense that the pressure drop across the heat exchanger should increase as the flow rate increases, but it might be surprising that the pressure drop across the valve decreases as the flow rate increases. The reason for this is that a change in the flow rate of liquid through the system corresponds to opening or closing the valve. If I close the valve completely, then the flow rate through the system is 0. The pressure drop across the heat exchanger is 0, and the entire 40 psi-G pressure drop is across the valve. Similarly, if I open the valve all the way or remove the valve so it offers no resistance to flow at all, then the pressure drop across the valve is 0, and the flow rate of liquid will increase until the pressure drop across the heat exchanger is the entire 40 psi G. That corresponds to a flow rate of 240 gallons per minute. And in between here, as we move back and forth along the curve, that corresponds to opening and closing the valve. As we go this way, we are closing the valve. As we close the valve, the flow rate through the system decreases, which causes the pressure drop across the heat exchanger to decrease, and the pressure drop across the valve increases because the valve is being closed. Similarly, or by contrast, as we go this way, we are opening the valve. The liquid flow rate increases, the pressure drop across the heat exchanger increases because the flow rate increases, and the pressure drop across the valve decreases because the valve is being opened. Okay, using the results on the previous slide, we can solve for the information requested in the example problem statement. For a linear valve that is half open at the design flow rate, our valve equation we can rearrange to solve for this valve coefficient. The valve coefficient is 200 divided by 0.5 times the square root of 10, which works out to 126.5 gallons per minute per psi raised to the power 1/2. These unusual units come from the definition of the valve coefficient in the equation on the previous slide. For an equal percentage valve that is sized to be completely open at 110% of the design flow rate, 110% of the design flow rate is 220 gallons per minute. From the equation on the previous slide, the pressure drop across the valve at 110% of the design flow rate is only 3.7 psi. And if the valve is completely open, the lift is equal to 1. And so our valve coefficient is given by this expression, 220 divided by the square root of 3.7, which is 114.4 gallons per minute per psi raised to the power 1/2. Okay, to summarize what we have said about control system instrumentation, for effective control, it is important to consider the characteristics of process sensors, signal conversion and transmission, and valve properties. Each of these steps will have an associated gain and may have dynamics as well. Control valves, as we have discussed, can be either air to open or air to close, and can also be either linear, quick opening, or equal percentage. And if we are designing a control valve, then the valve coefficient must also be specified.